Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins a luminous whirlpool of billions of stars, gas and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion, held together by a gravitational force so immense it defies comprehension. Yet, hidden within this stunning spectacle is an enigma. The visible elements of the galaxy stars, planets and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, Fritz Zwicky, a Swiss astrophysicist, observed that galaxies in the Coma cluster were moving faster than expected. By applying Newtonian physics, he calculated that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass providing the necessary gravitational glue. Decades later, Vera Rubin and Kent Ford confirmed this phenomenon within individual galaxies. Studying the rotation curves of spiral galaxies, they discovered something astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity, this was impossible unless there was an unseen mass extending far beyond the visible boundaries. This realization that most of the universe's mass is invisible reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality. What is this unseen force? How does it interact with the visible universe? And what does its existence mean for our understanding of life, existence, and everything in between? The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shape the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. And so, the quest begins with questions as vast and profound as the galaxies swirling in the night sky. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies, graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by the visible matter, you'd expect the stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense, star-filled core. However, observations tell a very different story. When Vera Rubin and her colleagues measured the rotation speeds of stars in spiral galaxies, they found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelops the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together, they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image, an unexpected star velocity, is a clue, bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not a theoretical abstraction, it is a tangible force shaping the universe. Its detection may be indirect, but its impact on the cosmos is undeniable. Dark matter is enigmatic not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible, capturing evidence of dark matter directly. The Large Hadron Collider, LHC, located at CERN in Geneva, is the world's most powerful particle accelerator. With its 27-kilometer ring buried underground, the LHC smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists at the LHC are particularly interested in detecting WIMPs, or weakly interacting massive particles, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data, escaping the detectors without interacting, much like neutrinos. While no conclusive evidence for dark matter has yet emerged from the LHC, the experiments have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters, as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies the Large Underground Xenon or Lux detector, one of the most sensitive instruments ever built to hunt for dark matter. Located in the Sanford Underground Research Facility in South Dakota, Lux relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with the xenon nucleus, it will produce a minuscule flash of light and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes, capable of detecting even the faintest whispers of activity. Although Lux has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, Lux Zeppelin, is even more advanced, with a larger detector and enhanced capabilities to sift through the cosmic silence in search of dark matter's elusive presence. Beyond the LHC and Lux, numerous other experiments contribute to the hunt for dark matter. Projects like Xenon 1T in Italy, PICO in Canada, and Super CDMS in the United States employ different approaches, from cryogenic detectors to bubble chambers, to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet, these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology which comes with significant costs. Facilities like the Large Hadron Collider and underground detectors like LUX or Xenon require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs dominate the conversation, other candidates such as actions, sterile neutrinos, and primordial black holes offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly reevaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments, like the upcoming Lux Zeppelin detector and advancements in neutrino observatories, are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to uncover the forces that bind the cosmos together, and to push beyond the boundaries of what is known. The Standard Model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions, the electromagnetic weak and strong nuclear forces. With the discovery of the Higgs boson in 2012, the Standard Model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem. The Standard Model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass energy content. This discrepancy has placed the Standard Model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The Standard Model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only Standard Model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter, but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the Standard Model for answers. Dark matter's invisibility stems from its apparent lack of interaction with electromagnetic forces. It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles like electrons or photons, which are central to the Standard Model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the Standard Model is incomplete. Several theories aim to bridge this gap, including supersymmetry. This theoretical framework extends the Standard Model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Hadron Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like actions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the Standard Model, it opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics, from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, or weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the action, a hypothetical particle much lighter than WIMPs. Actions arise from solutions to theoretical problems in the Standard Model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics. Unlike WIMPs, actions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes actions fascinating is their potential to form a vast, invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments such as the Action Dark Matter experiment aim to detect actions by searching for their predicted interaction with electromagnetic fields. Sterile neutrinos are an extension of the Standard Model's neutrinos, but differ in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. A more unconventional candidate for dark matter is primordial black holes. Unlike particle-based explanations, primordial black holes are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun and might account for at least part of the universe's dark matter. Although primordial black holes do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether primordial black holes could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, action sterile neutrinos, and primordial black holes, researchers explore other possibilities including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways. Fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter particles that interact with themselves but not with ordinary matter, potentially explaining certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while actions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass, interaction strength, or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years, and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past, it also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever, eventually freezing in a heat death, or contracts in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics, yet its influence is felt on the largest scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter particles could expose new forces or symmetries in nature, leading to extensions of the standard model. Astrophysics, understanding dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. Cosmology, insights into dark matter could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern technology, and quantum mechanics revolutionized our understanding of the universe. Similarly, understanding dark matter might reveal entirely new realms of physics, forces, or phenomena that we cannot yet imagine. In this sense, the discovery of dark matter is not just about solving a mystery, it's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures, dictating how galaxies form, cluster, and evolve over billions of years. Without dark matter, the cosmos as we know it would not exist. Understanding dark matter is therefore essential to refining our models of the universe's formation and its large-scale behavior. In the early universe, just after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as seeds for galaxy formation. Ordinary matter, composed of atoms, was initially scattered by intense radiation, but eventually fell into these dark matter wells, creating the galaxies and clusters we see today. Without dark matter, this process would have been impossibly slow, leaving a universe largely devoid of structure. Exploring dark matter is key to unraveling these early cosmic events. The universe is expanding, a fact first discovered by Edwin Hubble in the 1920s. Over time, this expansion has been found to be accelerating, driven by a mysterious force called dark energy. Dark matter and dark energy together dominate the universe, comprising approximately 95% of its total mass energy content. Their interplay shapes the dynamics of the cosmos. Dark matter slows the expansion through its gravitational pull, while dark energy pushes against it, driving acceleration. Understanding dark matter is critical to deciphering this delicate balance, the tug-of-war. How dark matter and dark energy interact influences the rate of cosmic expansion. Precise knowledge of dark matter's properties, its density, distribution, and interactions would allow cosmologists to make more accurate predictions about the universe's future trajectory. The ultimate fate of the universe, whether the cosmos ends in a big freeze, big crunch, or big rip, depends largely on the role and behavior of dark matter over cosmic timescales. The lambda called dark matter is the prevailing framework in cosmology. It describes a universe composed of dark energy, dark matter, and ordinary matter. While lambda called dark matter has been extraordinarily successful in explaining observations like the cosmic microwave background radiation and large-scale galaxy distributions, it remains incomplete without a deeper understanding of dark matter. Structure formation, simulations of galaxy and cluster formation depend heavily on assumptions about dark matter's properties. Better understanding could resolve discrepancies between observed and simulated galaxy distributions. Small-scale anomalies. The lambda-called dark matter model struggles to explain certain small-scale phenomena, like the observed density profiles of dark matter in galaxies. A deeper understanding of dark matter could address these inconsistencies. Studying dark matter may also provide insights into the universe's infancy. Shortly after the Big Bang, conditions were so extreme that matter and energy were indistinguishable. Dark matter's behavior during this epoch could reveal clues about the inflationary era, the rapid expansion of the universe immediately following the Big Bang. Baryogenesis, the process by which ordinary matter came to dominate over antimatter. Reionization, the period when the first stars and galaxies began to form, reionizing the universe's neutral hydrogen. By connecting the properties of dark matter to these events, cosmologists could fill gaps in our understanding of the universe's earliest moments. Dark matter research also has profound implications for understanding dark energy, the force driving cosmic acceleration. While these two phenomena are distinct, they are deeply intertwined in shaping the universe's fate. Studying dark matter may reveal new physics that unifies them, providing a more complete picture of the universe's mass-energy content and its ultimate destiny. Understanding dark matter would mark a paradigm shift in cosmology, akin to Copernicus' heliocentric model or Einstein's theory of general relativity. It would not only refine our knowledge of the universe's expansion, but also reveal the fundamental processes that govern the cosmos. By answering the question of dark matter, we edge closer to answering the larger questions. Where did we come from? Where are we going? And what is the true nature of reality? The discovery of dark matter would be a watershed moment for particle physics, opening a door to realms of knowledge far beyond the Standard Model. While the Standard Model has been remarkably successful in describing the known particles and forces, it cannot account for the mysterious substance that makes up 27% of the universe. This glaring gap suggests the existence of entirely new particles, forces, or symmetries that extend the boundaries of our current understanding. If dark matter is composed of particles, discovering its true nature could revolutionize our understanding of the subatomic world. Among the most promising avenues are WIMPs. Weakly interacting massive particles as leading candidates, WIMPs would represent a new class of particles interacting via weak nuclear forces. Their discovery could reveal new interactions and extensions to the Standard Model, such as supersymmetry, which posits the existence of partner particles for all known particles. Actions. The discovery of axions would solve not only the dark matter mystery, but also the strong CP problem in quantum chromodynamics. Actions could provide a bridge between particle physics and cosmology, unveiling connections previously thought unrelated. Sterile neutrinos. These hypothetical particles, unlike their Standard Model counterparts, would only interact through gravity. Detecting sterile neutrinos could expand our knowledge of neutrino physics and offer insights into the behavior of other elusive particles. Each of these particles represents a possible paradigm shift, revealing interactions or dimensions of nature that are currently hidden from view. Dark matter could point to the existence of previously unknown forces or interactions. For example, dark sector physics. Some theories propose that dark matter interacts with itself through dark forces mediated by particles analogous to photons in the visible universe. Detecting these forces could unveil an entirely new layer of reality, a dark sector that exists parallel to our observable universe. Fifth force of nature. If dark matter interacts with ordinary matter in unexpected ways, it might hint at a new, fundamental force beyond the four currently known: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. These discoveries would fundamentally alter our understanding of how the universe operates, potentially unifying disparate phenomena under a broader theoretical framework. One of the most profound implications of dark matter research lies in its potential to connect quantum mechanics and general relativity, two pillars of modern physics that remain theoretically incompatible. Dark matter operates on both quantum and cosmic scales, offering a rare opportunity to study phenomena that could unify these frameworks. If dark matter consists of quantum particles with wave-like properties, its behavior might illuminate how quantum effects manifest on macroscopic, gravitational scales. Understanding dark matter's gravitational effects could provide insights into quantum gravity, bringing us closer to a theory of everything. The hunt for dark matter has driven advancements in technology that benefit particle physics more broadly. High-energy experiments like those at the Large Hadron Collider are continually upgraded to achieve greater sensitivity, paving the way for discoveries beyond dark matter. Innovations in detector design, such as cryogenic techniques and ultra-pure materials, are already being applied to explore other unanswered questions in physics. These advancements not only enhance our ability to detect dark matter, but also improve our capacity to explore phenomena like neutrino oscillations, proton decay, and the asymmetry between matter and antimatter. The discovery of dark matter would necessitate extending the standard model to include new particles, interactions, and symmetries. Such an extension could reveal connections between seemingly unrelated phenomena, such as dark matter and the Higgs field, provide a framework for understanding other cosmic mysteries like dark energy or the origins of matter-antimatter asymmetry, offer insights into the conditions of the early universe, such as the processes that occurred during and after the Big Bang. The breakthroughs in particle physics spurred by dark matter research would ripple across multiple disciplines, from astrophysics to cosmology. These discoveries could redefine fundamental concepts such as mass, force, and even the nature of reality itself. As our theoretical frameworks evolve, so too will our ability to answer deeper questions about existence. As we conclude this journey through the unseen universe, one truth remains abundantly clear: dark matter is one of the greatest mysteries of our time. Its discovery and understanding hold the potential to reshape not only physics, but our very perception of reality. Yet, for all that we've explored its gravitational fingerprints, its hypothesized particles, and its role in the evolution of the cosmos, dark matter remains tantalizingly elusive. This mystery is a reminder of the vastness of the unknown. The universe is far larger, more complex, and more wondrous than we can currently imagine. Dark matter is but one piece of a much larger puzzle, one that includes dark energy, the origins of the universe, and the fundamental nature of existence itself. The ongoing quest to understand dark matter is a testament to human curiosity and ingenuity. It represents the best of science, a relentless pursuit of knowledge, driven by the belief that the answers lie just beyond our reach. With each experiment, each observation, and each theoretical breakthrough, we inch closer to uncovering the secrets of the cosmos. But dark matter is more than a scientific challenge, it's a source of inspiration. It invites us to dream, to question, and to wonder. What lies hidden in the fabric of the universe? What new realms of physics await discovery? How will these insights transform our understanding of the cosmos and of ourselves? The future of dark matter research is bright, filled with promise and potential. Advancements in technology, from more sensitive detectors to next-generation particle accelerators, bring us closer to direct detection. New telescopes and space missions will map the cosmos with unprecedented precision, revealing the subtle influences of dark matter on galaxies and beyond. Meanwhile, theoretical physicists continue to push the boundaries of what is possible, exploring ideas that might seem unimaginable today, but could become the discoveries of tomorrow. Each step forward in the hunt for dark matter deepens our understanding of the universe, reminding us that the pursuit of knowledge is never truly finished. As we unravel this mystery, we'll inevitably uncover new questions, new frontiers to explore, new challenges to face, and new wonders to marvel at. So, as we look to the future, let us embrace the mystery of dark matter. Let it remind us of the infinite possibilities that lie within the cosmos, waiting to be discovered. The journey to understand dark matter is far from over, but every step we take brings us closer to answering the fundamental questions of existence. What is the universe made of? Where did it come from? And what is our place within it? In the end, the greatest discoveries often begin with the simplest yet most profound realization: the universe is far more mysterious than we could ever imagine. And that mystery in itself is the ultimate source of wonder. Imagine standing beneath a vast starlit sky. The stars shimmer like distant embers, scattered across an infinite canvas. The night feels timeless, eternal, and yet, science tells us this grand spectacle has a story, one that began billions of years ago. But stories don't just begin, they also end. And so we must ask, will the universe itself come to an end? If so, how? This question is both humbling and haunting. What lies ahead for the cosmos? Will it fade into eternal darkness, collapse upon itself, or be ripped apart in a catastrophic finale? The universe, vast as it is, holds secrets about its ultimate destiny, and these secrets are written in the language of physics, a language we are only beginning to decipher. I think of the universe as a ticking clock. At its birth, with the Big Bang, the clock was wound up, its hands set in motion. Over billions of years, it has ticked forward, creating galaxies, stars, and even life itself. But like any clock, it may one day wind down. The question is, what does that final tick look like? Is it the silence of a stopped clock, or an explosion that shatters the mechanism entirely? We are not the first to ponder this cosmic mystery. For centuries, philosophers, scientists, and dreamers have gazed at the heavens and wondered about the end of all things. Today, armed with telescopes that peer billions of light years into space, and equations that reveal the universe's hidden workings, we have begun to glimpse possible answers. These answers paint a picture that is as awe-inspiring as it is unsettling. In this journey, we will explore the universe's potential fates. We'll begin with its origins, tracing the story of its expansion and the forces that drive it. Then we'll examine the leading theories about how it might all end, from a slow, freezing demise to a dramatic collapse or an ultimate ripping apart. Along the way, we'll pause to reflect on what these scenarios mean, not just for the cosmos, but for us, the tiny beings who dare to wonder about it. So, take a deep breath and prepare to dive into the ultimate question. What is the fate of the universe? And what might it reveal about our place within it? The answers may not be comforting, but they are certain to ignite your sense of curiosity and wonder. Because in the end, contemplating the universe's story is, in many ways, contemplating our own. Part 1. Understanding the universe's expansion. The Big Bang and aftermath. To understand the fate of the universe, we must first revisit its beginning, the Big Bang. Imagine an unimaginable singularity, a point smaller than an atom, but holding all the energy and matter that would become the universe. About 13.8 billion years ago, this singularity exploded, not into space, but creating space itself. Time began, energy burst forth, and the universe began its grand expansion. Evidence of this explosive beginning is all around us. One of the most compelling pieces is the cosmic microwave background radiation (CMB), often called the afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background radiation is a faint hum of energy that permeates the universe, a relic from when the cosmos was just 380,000 years old. It's as if the universe left behind an echo of its birth. Another key piece of evidence is redshift. When we observe distant galaxies, we see that their light shifts toward the red end of the spectrum. This redshift is caused by the stretching of light waves as the universe expands. Edwin Hubble's discovery of this phenomenon in the 1920s revealed a startling truth. Galaxies are moving away from us, and the universe is getting bigger. But what does this mean for the future? To answer that, we must understand not just that the universe is expanding, but how. Is this expansion slowing down, speeding up, or staying constant? These questions lead us to the mysterious force driving the cosmos's growth: dark energy. Think of the universe like a balloon. At the Big Bang, the balloon began to inflate. Over time, the rate of inflation has changed, influenced by the push and pull of different forces. Gravity, the force that pulls matter together, acts like a brake, trying to slow the expansion. But dark energy acts like an invisible hand, pushing the universe outward at an accelerating pace. This push and pull dynamic will shape the universe's ultimate fate. The story of the Big Bang is not just a story of beginnings. It's the first chapter in a larger cosmic narrative, one that sets the stage for the universe's possible endings. With the groundwork laid, we can now explore the scenarios scientists have envisioned for how this story might conclude. Current state: accelerating expansion. Today, scientists have discovered a surprising and critical truth. The universe's expansion is not just continuing, it's accelerating. This revelation came in the late 1990s, when two independent teams of researchers studying distant supernovae noticed something unexpected. The supernovae appeared dimmer than predicted, indicating that they were farther away than they should have been if the expansion rate were constant. This was the first evidence of an accelerating universe. The force driving this acceleration is known as dark energy, a mysterious entity that makes up about 68% of the universe. Dark energy is not well understood, but it acts as a kind of anti-gravity, pushing galaxies apart rather than pulling them together. Unlike matter or radiation, which diminish as the universe expands, dark energy's effects seem to grow stronger over time, dominating the universe's behavior on the largest scales. To grasp this, think of a race car. In the early universe, the expansion was like a car speeding up a hill, gravity working against it. But now, it's as if the car has reached the top and is speeding down an endless slope, propelled by an unseen force. This accelerating expansion has profound implications for the universe's fate. If dark energy continues to dominate, galaxies will drift farther and farther apart. Eventually, stars will burn out, leaving behind a cold, dark cosmos. This scenario, known as the Big Freeze or heat death, envisions a universe where all energy is spread so thin that no meaningful interactions can occur. Yet dark energy also raises questions. What is it? Is it constant, or could it change over time? Some theories suggest dark energy might grow even stronger, leading to a Big Rip scenario where galaxies, stars, and even atoms are torn apart. Others propose it might weaken, allowing gravity to eventually pull everything back together in a big crunch. The accelerating expansion is a reminder of how much we have yet to learn about the universe. It challenges our understanding of physics and pushes us to ask deeper questions about the forces that shape our reality. As we explore the possible endings of the cosmos, this enigmatic force will remain at the heart of the mystery. Part 2. Possible scenarios for the universe's end. Heat death, the Big Freeze. Among the possible endings for the universe, heat death stands as one of the most somber and inevitable scenarios. Imagine a cosmos where all the stars have burned out, their light extinguished, leaving behind only faint remnants like white dwarfs, neutron stars, and black holes. The universe, once vibrant and filled with activity, becomes a dark, cold void. This scenario is rooted in the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. In the context of the universe, this means energy will gradually spread out, becoming less and less useful for sustaining processes like star formation or even chemical reactions. Over trillions of years, galaxies will disintegrate as their stars fade away. The remaining particles of matter will drift apart, their movements slowing as temperatures approach absolute zero. To picture heat death, think of a campfire on a cold night. At first, the fire blazes brightly, radiating warmth and light. But as the fuel burns away, the flames shrink, the embers cool, and eventually, only ash remains. The universe, in this analogy, is the fire, and its energy is the fuel. Current models suggest that heat death is the most likely outcome if dark energy continues to dominate and the universe keeps expanding forever. In this eternal expansion, distances between galaxies will grow so vast that even light cannot bridge the gaps. Without sources of energy or interaction, the universe will enter a state of maximum entropy, a heatless death where nothing can happen. Yet the thought of heat death raises profound philosophical questions. If the universe ends in stillness, does that render all its past activity meaningless? Or does the beauty of the cosmos lie not in its ultimate fate, but in the journey, the stars, galaxies, and lives that once filled it with light and purpose? Heat death is not a sudden end, but a slow fading away, a whisper of the universe's former grandeur. It challenges us to reflect on time's inexorable march and the fleeting nature of existence. And while this gradual fading may seem bleak, it also offers a humbling perspective. The universe, like all things, follows its own natural course, a progression guided by laws we strive to understand. In the stillness of heat death, there is a quiet inevitability, a reminder of the fragility and transience of all that we hold dear. But perhaps the story doesn't truly end here. As with any grand narrative, every conclusion invites a new beginning. Might there be unseen mechanisms or phenomena yet to be discovered that could alter this trajectory? Could remnants of the universe's energy find a way to rekindle activity, defying the entropy that seems inevitable? The heat death scenario leaves us with these haunting yet beautiful questions, compelling us to cherish the universe in its current, vibrant state. After all, we are fortunate to exist in a fleeting moment of warmth, light, and life, a brief oasis in an otherwise indifferent cosmos. The Big Crunch. Now let's imagine a universe where expansion doesn't continue forever. Instead, gravity, the force pulling everything together, takes the upper hand. Over time, this opposing force could slow the universe's expansion and eventually reverse it, causing everything to collapse inward. This scenario is known as the Big Crunch. Picture the universe as a cosmic elastic band. For billions of years, the band stretches, expanding outward as galaxies drift apart. But at some point, the pull of gravity becomes too strong. The band snaps back, drawing all the galaxies, stars, and matter back toward a single, dense point, a dramatic reversal of the Big Bang. This potential outcome depends on the universe's total density, the combined mass and energy it contains. If the density is high enough to overcome the momentum of expansion, gravity will halt the outward push and trigger contraction. Scientists refer to this as a closed universe. As the universe contracts, the distances between galaxies shrink, temperatures rise, and stars collide in violent interactions. Eventually, everything converges into an unimitably dense and hot state, similar to the initial singularity that sparked the Big Bang. The cosmos could end where it began, leaving behind a singularity, or perhaps igniting another cycle of expansion in what some call a big bounce. But is the Big Crunch likely? Current observations suggest not. With dark energy driving accelerated expansion, the universe's density appears too low for gravity to reverse the trend. Nevertheless, the possibility of a cyclical universe remains an intriguing idea, raising profound questions. Could time itself restart? Are we part of an eternal loop of expansion and contraction? In this vision of cosmic destiny, the Big Crunch is both an ending and a potential beginning of fiery collapse that might give birth to another universe, starting the story anew. The Big Rip. Imagine a universe where the fabric of space-time itself tears apart. This dramatic scenario, known as the Big Rip, envisions an ending driven by the relentless growth of dark energy. Unlike other endings where gravity or entropy dominates, the Big Rip unfolds as dark energy grows stronger over time, ultimately overwhelming every force that holds the universe together. In this scenario, dark energy doesn't just accelerate the expansion of the universe, it accelerates it exponentially. Galaxies move farther apart at increasing speeds. Over billions of years, this acceleration becomes so extreme that it begins to tear apart galaxy clusters, then galaxies, and finally stars and planets. Even atoms, the fundamental building blocks of matter, are ripped apart in the final moments. To picture the Big Rip, think of a piece of fabric being stretched. At first, the stretching is gentle, but as the tension increases, the fabric begins to tear at its weakest points until it completely unravels. In this metaphor, the universe is the fabric, and dark energy is the force pulling it apart. This cataclysmic end would unfold as follows. 1. Billions of years before the end, galaxies are torn from one another as dark energy's influence grows stronger than gravitational forces. 2. Millions of years before the end, individual galaxies disintegrate, their stars flung into the void. 3. Moments before the end, stars, planets, and even atoms are pulled apart, leaving a universe devoid of structure or matter. The timeline for the Big Rip depends on the behavior of dark energy. Current models suggest dark energy is relatively stable, but if it grows more potent over time, a property physicists call phantom energy, the Big Rip becomes a viable outcome. This scenario raises profound questions. What happens when space-time itself is torn apart? Does time cease to exist? Could remnants of the universe persist in some form, or would reality itself end in complete dissolution? The Big Rip, while speculative, reminds us of the sheer power and mystery of dark energy, a force we are only beginning to understand. It is both a terrifying and awe-inspiring vision of the universe's potential fate, one where the end is not a gradual fading or a collapse, but an explosive tearing apart of everything that has ever existed. Part 3. Philosophical implications and unanswered questions. What does the end mean for life? What happens to life when the universe itself approaches its demise? This question forces us to confront not just the physical realities of cosmic endings, but their implications for existence. Life as we know it is bound by the conditions of the universe, its laws, its resources, and its time. But if those conditions change drastically, does life have a future? Consider heat death, where stars extinguish and the cosmos cools to near absolute zero. In such a scenario, even the most advanced civilizations might struggle. Imagine building a fire in a snowstorm that grows colder and darker by the moment. How could life persist in such relentless entropy? Yet history shows us the resilience of life. On Earth, extremophiles thrive in the harshest environments, deep sea vents, boiling hot springs, and even radioactive wastelands. Could life, or something like it, find ways to endure in the distant future? Perhaps intelligent species could harness energy from black holes or tap into quantum phenomena beyond our understanding. The possibilities stretch the limits of imagination. But what if even these strategies fail? Does the end of life in the universe mark a true ending? Or is there meaning in the brief moments of light and complexity that life brought to the cosmos? These are questions not just of science, but of philosophy, forcing us to ponder whether permanence is a prerequisite for significance. Could advanced civilizations escape these fates? If the universe's natural course leads to oblivion, could advanced civilizations find a way to defy it? Science fiction often speculates on such possibilities, but even speculative ideas are rooted in the boundaries of physics. One idea is the Dyson sphere, a colossal structure built to harness the total energy output of a star. Such technology could extend the lifespan of civilizations, allowing them to thrive even as the universe dims. But what happens when there are no more stars? Perhaps more radical are theories of escaping the universe itself. The concept of parallel universes or a multiverse suggests that our cosmos might not be alone. Could a sufficiently advanced civilization open portals to other universes, transferring their existence to a younger, more hospitable cosmos? If so, they might survive not just the end of this universe, but potentially any number of universal lifespans. Then there's the question of time itself. Some theories propose that time is not a fundamental property, but an emergent one, tied to the universe's structure. If time ends with the universe, what does that mean for beings within it? Could they find a way to live outside of time, in a state of timeless existence? Or would such a concept defy even the wildest reaches of imagination? What these speculations reveal is the boundless creativity of the human mind. The universe's end might seem inevitable, but as long as questions remain unanswered, the door is open to possibilities we have yet to comprehend. Perhaps the greatest lesson is not about survival, but about the resilience of curiosity, the drive to understand and adapt, no matter how daunting the challenge. Is time an illusion? If the universe ends, what happens to the concept of time? To explore this, we must first ask, what is time? For most of us, time is a constant, flowing river, a relentless current that carries us from one moment to the next. But is this river real, or is it an illusion shaped by our perception? Theories in physics suggest that time might not be fundamental but emergent, a byproduct of the universe's structure and processes. If the universe ceases to exist, does time dry up like a river evaporating under a scorching sun? Or does it persist in some form we cannot yet fathom? Consider the Big Freeze, where the cosmos becomes a static, cold expanse. Without events or motion to mark its passage, what meaning does time have? In the Big Rip, where everything disintegrates into its smallest components, could time itself unravel, reduced to a meaningless concept? Time, in this sense, is deeply tied to change. It is the rhythm of the universe's dance, the beats of stars being born, galaxies colliding, and life evolving. Without change, the melody ceases. Does this mean time is merely an artifact of motion, a measure of the universe's activity? Or is it something more profound? The idea of time's end also raises philosophical questions. If time has a beginning and an end, is it a finite resource, like sand slipping through an hourglass? Or is it cyclical, a loop that resets with each new cosmic cycle, as some theories of the multiverse suggest? Could we ever exist outside of time, experiencing reality in a way that transcends our linear understanding? These questions remind us of the enigmatic nature of time. Whether it's an illusion, a dimension, or something entirely beyond our comprehension, its fate is inextricably linked to the universe's destiny. Time is the silent witness to all cosmic events, and pondering its end forces us to confront the ultimate mystery of existence itself. Are there cycles? Could the universe itself be part of an eternal cycle, dying and being reborn like a cosmic phoenix rising from its ashes? This idea lies at the heart of cyclic models, which suggest that the universe's end might not be a conclusion, but a prelude to a new beginning. One such model is the Big Bounce, a theory that envisions the universe contracting after its expansion reaches a peak. Instead of collapsing into a singularity as in the Big Crunch, the universe rebounds, triggering another Big Bang. This cycle of expansion and contraction could repeat indefinitely, creating an endless loop of cosmic rebirth. Another perspective comes from multiverse theories. These suggest that our universe is just one of countless others, each with its own birth and death. If universes can emerge from the remnants of others, could our cosmos be part of an interconnected web of existence, where endings are never absolute but merely transitions? The metaphor of a phoenix captures this concept beautifully. Like the mythical bird that perishes in flames only to rise anew, the universe could regenerate from its own demise. Each cycle would erase the past while laying the groundwork for future possibilities, an eternal dance of destruction and creation. But how might such cycles occur? Could remnants of the current universe, black holes, quantum fluctuations, or even dark energy seed the conditions for a new one? The details remain speculative, yet they ignite profound questions about the nature of existence. If cycles are real, is there a purpose to them? Do they follow a grand design, or are they random acts in an infinite cosmic play? Cyclic models challenge us to think beyond linear timelines and finite conclusions. They suggest a universe that, like a heartbeat, pulses with life and renewal. And while we may never witness these grand cycles, contemplating them reminds us of the vast possibilities that lie within the cosmos. Perhaps, in the universe's story, there are no true endings, only endless beginnings. Throughout this journey, we've explored the universe's potential fates. From the chilling stillness of heat death to the fiery collapse of the Big Crunch, the violent unraveling of the Big Rip, and the hopeful renewal of cyclic models. Each scenario presents profound questions about existence, time, and the nature of reality itself. But does the end of everything mean the end of meaning? Perhaps not. Meaning is not solely derived from permanence. It often lies in the fleeting, the transient, the moments that shape our experience of the cosmos. The stars that shine above us, the life that thrives on Earth, and the curiosity that drives us to seek answers, these are what define our place in the universe. As we contemplate the universe's story, we must embrace its uncertainties. The vastness of the cosmos humbles us, reminding us of our small yet significant role as observers and thinkers. Whether the universe ends in silence, destruction, or rebirth, its journey inspires awe and wonder. So, as you look up at the stars, remember this: the universe's greatest mystery is not just in how it ends, but in how it compels us to question, to dream, and to seek understanding. And in that pursuit, we find meaning not in answers, but in the act of asking. Imagine this: a butterfly flaps its wings in the dense Amazon rainforest. Its delicate motion stirs the air, setting off a chain of events that eventually leads to a storm forming on the other side of the world. This might sound like poetry or fantasy, but it touches upon something deeply profound, a question that has captivated scientists, philosophers, and spiritual thinkers for centuries. Could every action, no matter how small, truly ripple outward in ways we can scarcely imagine? Could the universe itself be a vast, interconnected web where everything is bound together by invisible threads? In our day-to-day lives, it's easy to see ourselves as isolated beings, each pursuing our own path, each grappling with our own concerns. Yet, beneath the surface, the world reveals a different story, one of profound interconnection. Every thought, every choice, every particle of matter seems to be part of a larger whole. To explore this idea is to venture into the heart of existence itself, to ask what it truly means to be a part of this vast, mysterious system we call reality. Why does this matter? In a world that feels increasingly fragmented, where global crises collide with individual struggles, understanding the threads that bind us can reshape how we see ourselves and each other. It challenges us to think beyond borders, beyond personal interests, and even beyond the limitations of our senses. Whether through the lens of science, philosophy, or our daily lives, the idea of interconnection offers not only insights into the workings of the universe, but also guidance on how to live within it. Let's begin with an experiment of imagination. Picture a spider's web stretching endlessly in all directions. At each intersection lies a shimmering drop of dew, reflecting every other droplet on the web. A single vibration, no matter how faint, ripples through the entire structure. Now, replace the silk threads with atoms, ecosystems, and human relationships. This is not just an image, but a metaphor for the reality we inhabit, a world where every movement, no matter how small, resonates across the whole. As we delve deeper into this idea, we'll journey through the realms of cutting-edge science, uncover the echoes of ancient wisdom, and draw connections to the choices we make every day. Along the way, we'll confront questions that defy simple answers. How does the universe remain so interconnected despite its vastness? Can the actions of a single individual ripple outward to shape the destiny of others, or even the planet? And if all things are truly connected, what responsibilities do we bear as part of this intricate web? This journey is not just about understanding the world, it's about finding our place within it. So, let's explore this profound question together. What does it mean to live in a universe where everything is connected? Let us dive into the science of interconnection, where the universe reveals its most intriguing secrets. At the heart of modern physics lies a phenomenon so strange that even Einstein himself called it spooky action at a distance. Quantum entanglement, this mysterious connection between particles, has challenged the way we understand reality. When two particles become entangled, their states are linked in such a way that a change in one instantly affects the other, regardless of the distance between them. Imagine this: two twins, separated by galaxies, yet if one raises a hand, the other does the same at the exact moment. This isn't a thought experiment, it's a proven reality. Scientists have measured entangled particles separated by over 1,200 kilometers, showing that their connection defies the classical boundaries of time and space. What does this mean for us? It suggests that the universe may not be as fragmented as it appears. Instead, it hints at a deeper, unified reality, one where everything may be fundamentally connected. If, as some physicists propose, all particles in the universe were entangled at the moment of the Big Bang, it's not entirely unreasonable to wonder, are we still connected to the stars, the planets, and each other? But interconnection isn't confined to the quantum realm. Nature itself demonstrates this principle on a grander scale. Consider a meadow alive with buzzing bees and blooming flowers. This idyllic scene is underpinned by a complex web of interdependence. Bees pollinate plants, enabling them to reproduce. Plants provide food and oxygen for countless organisms. Animals, in turn, spread seeds, ensuring the survival of future generations. Disrupt any part of this system, and the consequences ripple outward. If the bees vanish, crops fail. If the forests fall, the climate changes. These connections are not abstract, they are the very fabric of life on Earth. And yet, the connections go deeper still. In the 1960s, meteorologist Edward Lorenz discovered what he called the butterfly effect. A small, seemingly insignificant action, like the flap of a butterfly's wings, can set off a chain of events, leading to vastly different outcomes, like a hurricane forming halfway across the world. This principle, rooted in chaos theory, reveals that even the most unpredictable systems, such as weather or financial markets, are governed by underlying patterns. What begins as a whisper can grow into a roar. This ripple effect isn't limited to science or nature, it extends into our lives and our choices. History is full of moments where small actions led to monumental changes. A single decision, a conversation, or even a chance meeting has the potential to alter the course of history. It's a reminder that what we do matters, even if we cannot always see the full extent of our impact. As we reflect on these scientific revelations, one truth emerges: nothing exists in isolation. From the entangled particles of quantum physics to the ecosystems that sustain life and the patterns of chaos that shape our world, interconnection is not just an idea, it's the reality of the universe. But this understanding is not new. Across centuries and cultures, ancient philosophies and spiritual traditions have explored this same truth in their own profound ways. Let's turn now to the wisdom of the past and discover how it aligns with the discoveries of modern science. Throughout history, the idea of interconnection has been a cornerstone of philosophical and spiritual thought, particularly in the traditions of the East. Hinduism and Buddhism, for example, offer vivid metaphors that echo the interconnectedness we now explore through science. One of the most compelling is the concept of Indra's net, an ancient image describing a vast, cosmic web that stretches infinitely in all directions. At each intersection of this net lies a jewel, and each jewel reflects every other jewel. The implication is profound: every part of the universe is linked, and the whole is reflected in each individual part. This imagery is strikingly similar to modern ideas of holography, where every fragment contains the entirety of the image. It also aligns with quantum physics, where particles, no matter how distant, are fundamentally connected. Such parallels suggest that ancient wisdom may have intuited truths that science is only now beginning to uncover. Buddhism offers another perspective through its principle of dependent origination, which states that nothing exists independently. Everything arises from a network of causes and conditions. Consider a tree. It isn't just a tree, it's sunlight, rain, soil, and time. Remove any one of these, and the tree cannot exist. This understanding extends beyond physical objects to encompass human experiences, relationships, and actions. Recognizing this interdependence fosters compassion, as it highlights how our choices inevitably affect others. Similarly, Taoism emphasizes harmony through unity. The Taoist worldview sees the universe as a single, harmonious entity where opposites yin and yang are not in conflict but in balance. To live well, Taoism teaches, is to flow with this interconnected rhythm of life, acting in harmony with the natural order rather than against it. While Eastern traditions embrace unity as a core truth, Western thought has approached interconnection through reason and observation. The 17th century philosopher Baruch Spinoza proposed a radical idea that everything in the universe is part of a single, infinite substance, which he called God or nature. Spinoza argued that distinctions between self and other, or mind and body, are illusions. All things are manifestations of the same underlying reality. This philosophy resonates with modern physics, particularly the idea of a unified field from which all forces and particles arise. More recently, the Gaia hypothesis, developed by James Lovelock, offers a scientific perspective on interconnection. According to this view, Earth functions as a single, self-regulating organism. The planet's atmosphere, oceans, and ecosystems work together to maintain conditions for life. Disruptions in one system, deforestation, pollution, or the loss of biodiversity affect the entire balance. This perspective underscores humanity's responsibility to act as stewards of this interconnected web, recognizing that harming the Earth ultimately harms ourselves. Across cultures, spiritual traditions also echo the idea of humanity's place within a larger cosmic network. Many indigenous beliefs regard nature as sacred and humans as caretakers rather than masters. For example, Native American teachings often emphasize the importance of acting in harmony with the Earth, knowing that every action ripples outward through the web of life. Similarly, Carl Jung's concept of the collective unconscious proposes that humanity shares a reservoir of archetypes, universal symbols, and themes that shape our myths, dreams, and cultures. These shared patterns suggest a psychological connection that transcends individual experience, linking us to one another in profound ways. What emerges from these philosophies, both ancient and modern, is a vision of unity, one that challenges the perception of separateness and celebrates the intricate web of existence. But this understanding isn't limited to abstract thought. It manifests in our daily lives, shaping our relationships, societies, and choices. Let us now turn to the human sphere and examine how interconnection plays out in the world we inhabit every day. In our daily lives, the interconnected web of existence reveals itself most vividly through human relationships and the societies we build. While the threads may seem invisible, they shape every aspect of how we live, think, and act. Take, for instance, the idea of 6 degrees of separation, the theory that every person on Earth is connected to any other by no more than 6 steps. Originating from a social experiment in the 1960s, this concept has since been supported by network science and modern technology. In today's world, social media and global communication have made these connections even more immediate, shrinking the degrees of separation and creating a sense of closeness that transcends physical distance. This interconnectedness isn't just about proximity, it's about influence. Research in social networks shows that emotions, behaviors, and even health can ripple through communities. Happiness, for example, has been found to spread across social circles, with one person's joy increasing the likelihood of happiness in their friends' friends, and beyond. Similarly, negative habits like smoking or overeating can propagate through networks, showing how deeply our actions affect others, often far beyond our direct interactions. Beyond personal relationships, there exists a deeper, collective connection that transcends time and space. Carl Jung's theory of the collective unconscious suggests that humanity shares a repository of universal symbols and archetypes, images, and ideas that appear across cultures, from ancient myths to modern storytelling. These shared patterns hint at a profound psychological connection, where individual minds tap into a collective reservoir of human experience. Consider how the hero's journey, a narrative structure described by Joseph Campbell, appears in myths from every corner of the world, from Homer's Odyssey to Star Wars. Such universality speaks to a shared cultural and spiritual heritage that binds us together. Cultural transmission, or the exchange of ideas and practices, further highlights our interconnection. British scientist Richard Dawkins coined the term meme to describe units of cultural information, traditions, innovations, or even jokes that spread and evolve like genes. Whether it's the global adoption of yoga or the viral spread of social justice movements, these cultural memes demonstrate how ideas traverse borders, connecting humanity in ways that physical presence never could. Yet our interconnectedness extends beyond culture to the very foundations of modern civilization. Globalization has made it abundantly clear that no nation or community exists in isolation. A financial crisis in one country can send shockwaves across the globe, as seen during the 2008 economic downturn. Supply chains, too, illustrate how deeply economies are intertwined, with products often relying on contributions from multiple countries before reaching the consumer. While this interdependence has brought unprecedented prosperity, it also reveals vulnerabilities. Environmental degradation, pandemics, and climate change are stark reminders that global challenges demand collective solutions. This interconnected reality underscores the power of individual and collective actions. Consider the ripple effect of small, positive choices. A single tweet can spark a global movement, as seen with Me Too, where millions shared their stories, reshaping cultural conversations about harassment and power dynamics. Grassroots environmental efforts, such as local reforestation projects, can inspire broader initiatives, influencing policy at national and international levels. These examples remind us that even the smallest actions can reverberate far beyond their origin, influencing the shape of the world we all share. But interconnection is not without its challenges. In a world so tightly woven, how do we balance individual needs with collective responsibilities? How do we ensure that the actions we take, no matter how well-intentioned, strengthen rather than strain the web of life? These are questions that demand careful reflection, but they also offer a powerful opportunity to live with awareness, compassion, and purpose. As we acknowledge the profound ways we are connected, one thing becomes clear: the choices we make matter. Whether it's in how we treat the planet, how we interact with others, or how we approach the challenges of our time, our actions ripple outward, shaping the interconnected web of existence. Let's now explore the practical implications of this understanding and consider how we can act in ways that honor and sustain the connections that bind us all. The realization that everything is interconnected is more than a philosophical or scientific insight, it's a call to action. This understanding transforms how we relate to the environment, to each other, and to ourselves. It urges us to take responsibility for the threads we touch, knowing that our actions can reverberate far beyond our immediate surroundings. Take the environment, for example. Every ecosystem is an intricate web of interdependence, and any disruption in one part of the system has consequences for the whole. Deforestation in the Amazon affects global weather patterns. Plastic waste dumped into the ocean doesn't just pollute the water, it breaks down into microplastics that enter food chains and eventually our bodies. These examples remind us that environmental harm in one region is never truly isolated, it ripples outward, affecting people and ecosystems worldwide. Recognizing this, global challenges like climate change or biodiversity loss demand collective action. Initiatives such as the Paris Agreement reflect an acknowledgement of interconnection, bringing nations together to address shared threats. Yet the responsibility doesn't rest solely on governments or institutions. Individual actions reducing waste, supporting renewable energy, planting trees can contribute meaningfully to global solutions. Each choice, however small, becomes a thread in the greater tapestry of change. But interconnection isn't only about the natural world, it's also about the choices we make in our relationships and communities. In a connected society, even minor acts of kindness can have profound effects. A simple gesture of empathy can inspire others to do the same, creating a ripple of positivity that extends far beyond its origin. On a larger scale, grassroots efforts, community cleanups, volunteer programs, or social campaigns demonstrate how collective action can lead to meaningful change. These ripples may start small, but they have the potential to grow, influencing policies, cultural norms, and even global movements. Technology amplifies these connections in powerful ways. Social media, for instance, allows ideas to spread at unprecedented speed. A single post can inspire millions to take action, whether it's raising funds for disaster relief or mobilizing support for social justice causes. At the same time, technology also poses challenges, such as the spread of misinformation or the environmental cost of digital infrastructure. Acknowledging interconnection means using these tools responsibly, ensuring that they strengthen the web rather than weaken it. This understanding also challenges us to think differently about responsibility. In a fragmented worldview, it's easy to feel isolated, to believe that individual actions are insignificant in the face of global issues. But interconnection reveals a deeper truth. Every action matters because it is part of a larger whole. This doesn't diminish individual importance, it amplifies it, showing how small, mindful choices contribute to the collective good. With this shift in perspective, we begin to see the world not as a series of isolated problems, but as a dynamic, interwoven system. Environmental stewardship becomes a moral imperative, not because of abstract principles, but because our survival and well-being are directly tied to the health of the planet. Collaboration and compassion become essential in addressing social challenges, not as acts of charity, but as expressions of the fundamental truth that our lives are intertwined. Yet, interconnection also calls for balance. It's easy to feel overwhelmed by the vastness of the web, by the weight of realizing that every action matters. The challenge lies in finding agency within this complexity. We don't need to solve every problem or touch every thread. Instead, we can focus on the parts of the web closest to us, trusting that our contributions will resonate outward. This is the power of interconnection. It reminds us that we are never truly alone, that every action has meaning, and that together we weave the fabric of existence. But not everyone sees it this way, and this understanding is not without its challenges. Let's turn to the critiques and difficulties of embracing interconnection and explore how they shape our understanding of this profound concept. While the idea of interconnection is compelling, it is not without its skeptics and challenges. Critics often question whether all connections are meaningful, or if humans are simply pattern-seeking creatures, prone to finding links where none exist. It's a valid concern. Our brains are wired to make sense of the world, to organize chaos into familiar patterns, even when those patterns might be coincidences. Consider how we might see a streak of good luck as a sign of destiny, or interpret unrelated events as having a deeper, hidden connection. Is interconnection truly real, or are we assigning meaning to randomness? This skepticism is compounded by the limits of human perception. Even if the universe operates as a connected system, our ability to comprehend it is inherently restricted. The scales of interconnection, ranging from the quantum to the cosmic, are far beyond what our senses or intuition can grasp. Quantum entanglement, for example, defies everyday understanding, as particles communicate instantaneously across vast distances. Similarly, ecosystems and weather patterns are governed by such intricate dynamics that even our most advanced models struggle to predict them with precision. Another challenge lies in the practical application of interconnection. While it's easy to embrace the idea on a philosophical level, turning it into actionable change is far more complex. Global collaboration often falters in the face of competing interests. Climate agreements, for instance, reflect the difficulty of aligning nations with differing priorities, resources, and responsibilities. Even on an individual level, the emphasis on personal responsibility can sometimes feel overwhelming. If every choice matters, how do we avoid being paralyzed by the weight of our decisions? How do we reconcile the vastness of our potential impact with the smallness of our everyday lives? Scientific exploration of interconnection also faces its own hurdles. While quantum entanglement is well documented, its application to larger systems remains speculative. Can the principles of quantum mechanics truly explain interconnection on human or societal scales? Chaos theory, too, reveals the complexity of dynamic systems but leaves many questions unanswered. For example, while we understand that small changes can lead to massive effects, predicting or controlling these outcomes remains elusive. Philosophically, interconnection raises tensions between unity and individuality. If all things are one, where does that leave personal identity and autonomy? This question is particularly challenging in societies that value individualism. Balancing the needs of the collective with the rights of the individual is a delicate task, one that becomes even more complicated when applied to real-world issues like governance, resource distribution, or cultural preservation. There's also the risk of feeling powerless in the face of such vast systems. Acknowledging interconnection can evoke awe and wonder, but it can also inspire a sense of insignificance. How much influence does one person truly have within such an intricate web? This tension between agency and complexity is one of the central challenges of embracing interconnection as a guiding principle. Despite these critiques, the idea of interconnection remains a powerful lens through which to view the world. It's not about proving every connection or solving every problem. Instead, it's about cultivating curiosity, humility, and a willingness to engage with the complexity of existence. Even when the web seems too vast to comprehend, each thread we touch still resonates. As we grapple with these challenges, it becomes clear that they are not obstacles to interconnection, but part of its profound mystery. They remind us that understanding the universe and our place within it is an ongoing process, one that invites us to think deeply, act consciously, and remain open to the unknown. With this perspective, let us now reflect on the journey we've taken and draw it together in a final contemplation of the web of existence. As we reach the conclusion of this exploration, it's worth pausing to reflect on the journey we've undertaken. We began with a simple yet profound question: are all things truly connected? Along the way, we've unraveled threads from the fabric of science, philosophy, and human experience, each revealing a different facet of the web of existence. In the realm of science, quantum entanglement showed us how particles, separated by vast distances, can remain mysteriously linked, challenging our understanding of time, space, and causality. Nature's ecosystems demonstrated that interdependence isn't a theoretical idea, but the foundation of life on Earth, where the health of a bee can ripple outward to affect entire food systems and climates. The butterfly effect reminded us that small actions can lead to massive consequences, not only in physical systems but in human history and culture. Philosophy and spirituality echoed these truths, offering ancient metaphors like Indra's net to describe the unity of existence. Eastern traditions emphasized the interdependence of all things, while Western thinkers like Spinoza and Lovelock revealed a similar vision of interconnectedness through reason and science. Human societies, too, provided vivid examples of interconnection, from the spread of cultural memes to the shrinking world created by globalization and technology. This journey has also confronted us with challenges: the limits of human perception, the complexities of large systems, and the tension between individuality and unity all remind us that interconnection is not always easy to grasp or act upon. Yet these challenges don't diminish the significance of the web, they deepen it. They invite us to approach the world with humility, recognizing that we are part of something far greater than ourselves. So what does all this mean for how we live? Recognizing interconnection reshapes our understanding of responsibility. It teaches us that every choice we make, what we consume, how we treat others, how we care for the planet resonates far beyond its immediate context. This awareness isn't a burden, it's an opportunity. It allows us to act with intention, knowing that even small, thoughtful actions can contribute to a larger ripple of positive change. It also offers a new perspective on challenges. Problems that once seemed insurmountable, climate change, inequality, or even personal struggles, can be reimagined as shared endeavors. Interconnection reminds us that we are not alone, that solutions require collective effort, and that our individual contributions, however small, matter. But perhaps the most profound gift of interconnection is the way it shifts our sense of belonging. We are not isolated fragments, adrift in a cold, indifferent universe. We are threads in a tapestry, each part of a larger story. This realization brings both comfort and responsibility, comfort in knowing we are never truly alone, and responsibility in acknowledging that we shape the web through our thoughts, actions, and relationships. As we close, let's return to the question that began this journey: are all things truly connected? Science, philosophy, and human experience suggest the answer is yes. But more important than the answer is the question itself, for it invites us to see the world and ourselves with fresh eyes. If everything is connected, what will you do with this knowledge? How will it change the way you live, the way you think, and the way you contribute to the web of existence? The threads of the universe stretch infinitely in all directions. You are one of them. What kind of ripple will you create? Does reality truly exist if no one is observing it? How can two particles on opposite sides of the universe instantly influence each other? Is it possible that every decision we make creates a parallel universe? If time can reverse at the quantum level, what does that mean for our future? Could the human brain operate like a quantum computer? Are we living in a reality where everything is invisibly interconnected? Welcome to the perplexing world of quantum mechanics, where the rules we think govern reality break down, and the universe reveals itself as something far stranger than our everyday experience suggests. The mysterious truths of quantum mechanics. Imagine tossing a pebble into a pond. The ripples spread out, graceful and predictable. Now, what if the pebble could behave both like a ripple and as a solid object at the same time? Quantum mechanics is a branch of physics that studies the smallest building blocks of the universe, particles like electrons, photons, and quarks. Yet the more we look, the less solid reality seems to become. This section will explore three of its most mysterious phenomena: wave-particle duality, superposition, and quantum entanglement. Wave-particle duality is the idea that light and matter can behave both as particles and waves, depending on how they're observed. Imagine asking someone whether a coin is heads or tails, and their answer changes depending on how closely you're looking. The double-slit experiment. In this iconic experiment, scientists shot particles, like electrons or photons, at a barrier with two slits. Behind the barrier was a screen to capture where the particles landed. Step 1. When the particles were observed closely, they behaved like tiny marbles, forming two distinct lines on the screen, one behind each slit. Step 2. When not observed, the particles acted like waves, spreading out and forming an interference pattern of many lines, as though the particles had passed through both slits simultaneously and interfered with themselves. Simplified explanation. Think of a particle as a traveler facing a fork in the road. When no one is watching, the traveler takes both paths at once, exploring every possibility. But the moment you watch, the traveler chooses one path, as if responding to your gaze. Why it's strange? This suggests that the mere act of observing can change the fundamental behavior of matter. Is reality shaped by observation? And if so, what does that mean about the universe when no one's watching? Quantum superposition. In classical physics, an object is either here or there, in one state or another. Quantum mechanics introduces superposition, where particles exist in multiple states simultaneously until measured. Schrödinger's cat thought experiment. A physicist, Erwin Schrödinger, imagined placing a cat in a box with a vial of poison, which would break if triggered by a random quantum event. Until someone opens the box, the cat exists in a superposition of states both alive and dead. Imagine flipping a coin and sealing it inside an envelope. To you, the coin is both heads and tails at the same time, because you haven't seen it yet. It's only when you open the envelope that the coin chooses a side. Why it's strange, superposition challenges the idea of objective reality. If particles exist in multiple states until observed, is the universe inherently uncertain? And how does reality decide which state to take when observed? Quantum entanglement. Entanglement occurs when two particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are, even if they're on opposite sides of the universe. Einstein's skepticism. Albert Einstein famously called entanglement spooky action at a distance, because it seemed to defy the speed of light, the universal speed limit. Yet experiments have repeatedly confirmed this phenomenon. Simplified metaphor, imagine you have a pair of gloves. You send one glove to the moon and keep the other on Earth. Without looking, you don't know which is the left glove and which is the right. The moment you check the glove on Earth and see it's the left one, you instantly know the glove on the moon is the right, even though no information traveled between them. Entanglement suggests that particles can remain connected in a way that transcends space and time. Could this imply a deeper, hidden layer of reality where everything is interconnected? Questions to ponder. If observing particles changes their behavior, does that make us co-creators of reality? How can particles influence each other instantaneously across vast distances? Is the universe fundamentally random? Or is there an underlying order beneath the quantum chaos? Quantum mechanics challenges our deepest assumptions about reality. Wave-particle duality blurs the lines between objects and actions. Superposition raises questions about the nature of existence, and entanglement hints at a universe where everything is interconnected in ways we're only beginning to grasp. This is just the beginning of our journey into quantum science. As we dive deeper, these mysteries will intertwine with questions of philosophy, consciousness, and the very fabric of time. But for now, quantum mechanics reminds us of a humbling truth. The universe is far stranger and far more wonderful than we ever imagined. Philosophy and quantum mechanics. Quantum mechanics doesn't just alter our understanding of physics. It challenges our fundamental beliefs about reality, existence, and the nature of the universe. It brings us face to face with questions that philosophers have grappled with for centuries. Could quantum mechanics provide the missing link between science and philosophy? In this section, we explore the fascinating relationship between quantum theory and philosophical inquiry. The observer effect. Does reality exist without observation? The observer effect in quantum mechanics suggests that the mere act of observing a quantum system can change its behavior. In the famous double-slit experiment mentioned earlier, particles like electrons or photons behave as waves when unobserved, and as particles when observed. But here's the philosophical twist. If observation affects reality, then can we really say that the world exists independently of us? Does the universe only decide its state when we look at it? This is a powerful philosophical question that echoes the debate about whether existence requires a mind to perceive it. Simplified explanation. Imagine you're trying to catch a butterfly in the wild. Every time you approach it, the butterfly flutters away, changing its position and behavior. If you stand still and don't try to catch it, the butterfly behaves in its natural way. The act of trying to catch it or observe it changes what it does. This is like what happens at the quantum level. Our attempt to measure something changes its state. Philosophical connection. This idea mirrors solipsism, a philosophical theory that suggests only the mind of the observer can be known to exist. In quantum mechanics, it's almost as if reality isn't truly there until we observe it. Could our minds actually be shaping the world around us? If so, what does that say about free will and our place in the universe? Questions to ponder. If the act of observing creates reality, what does that say about the world when we're not looking? Can we ever truly know the universe if our perception of it always shapes it? The multiverse hypothesis, a universe for every possibility. Quantum mechanics also suggests that, when faced with multiple possible outcomes, particles don't just pick one, they exist in all possibilities simultaneously until measured. This leads to the many worlds interpretation, which proposes that every time a quantum event occurs with multiple possibilities, the universe splits into separate branches, each representing one of the possible outcomes. Essentially, every decision, every quantum event creates a new universe. Simplified explanation. Imagine you have a coin and you're about to flip it. In the quantum world, the coin doesn't just land on heads or tails, it lands on both, in separate worlds. In one universe, it's heads, in another, it's tails. Every possible outcome of every quantum event exists in its own parallel universe. This theory raises the idea of determinism versus free will. If every possible outcome exists in a parallel universe, does that mean we're simply along for the ride, with no true choice? Or does the fact that we experience one outcome imply that we are actively shaping our reality? Questions to ponder. If there are infinite universes, does it mean all possibilities are actualized, or is there still a guiding hand behind it all? What does this say about the role of free will in our lives? Are we simply living out one branch of the many possibilities? Determinism versus free will. Does the quantum world allow for both? In classical physics, the universe was thought to be deterministic. Everything happens because of prior causes, like the turning of a clock. But quantum mechanics doesn't fit this model. Quantum mechanics tells us that at the microscopic level, events are not entirely predictable and chance plays a significant role. This creates an interesting paradox when thinking about human behavior. Is everything determined by the laws of physics, or do we have the power to make choices that aren't preordained? Think of a rolling dice. Classical physics would say the dice's outcome is determined by its starting position, how fast it rolls, and all the forces acting on it. But in quantum mechanics, the dice could land on several faces at once, and it's only when we look at it that we see which face it lands on. Could our decisions be more like this quantum roll of the dice? This aligns with a long-standing philosophical debate. Is our universe deterministic, where everything happens for a reason, or is there room for randomness and free will? Quantum mechanics, with its inherent unpredictability, seems to suggest that randomness plays a role in shaping our world. But what does that mean for the human experience of choice? Questions to ponder. If quantum mechanics allows for randomness, does that free us from being controlled by the laws of physics, or does it create a different kind of order? How does this randomness relate to the concept of free will? If we're free to choose, is it random, or is there a deeper purpose behind our decisions? In this section, we've explored how quantum mechanics doesn't just change our view of the universe, it compels us to revisit age-old philosophical questions. From the observer effect's challenge to objective reality, to the multiverse's implications for free will, quantum theory forces us to reconsider what we think we know about existence. Quantum mechanics isn't just a tool for physicists, it's a bridge between science and philosophy, urging us to ask deeper questions about the nature of reality, consciousness, and choice. As we continue to explore these ideas, we'll see how quantum mechanics intertwines not only with the smallest particles, but also with the deepest questions about our place in the cosmos. Quantum mechanics and consciousness. The intersection between quantum mechanics and consciousness is one of the most intriguing and speculative areas in modern science. Does quantum theory hold the key to understanding consciousness? Could our minds be operating on quantum principles, giving rise to thoughts, emotions, and self-awareness? This section explores how quantum mechanics might be connected to the very nature of consciousness, blurring the lines between physics, philosophy, and psychology. Quantum brain hypothesis. Could the brain work like a quantum computer? One fascinating theory is that the brain could operate like a quantum computer, using the principles of superposition and entanglement to process information in ways classical computers can. The idea is that quantum effects might be occurring within our neurons, influencing how we think, perceive, and experience the world. Imagine trying to solve a puzzle by checking all the possible answers one at a time. A classical computer would do this in a linear fashion, one possibility after another. But a quantum computer, using superposition, could check all possibilities at once much faster. If our brains work this way, it could explain the speed and complexity of human cognition. Supporting evidence. Some scientists point to microtubules, tiny structures within our neurons, as potential quantum processors. These microtubules might be able to support quantum states, which could allow the brain to process vast amounts of information at incredible speed. The hypothesis was notably proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff in their theory of orchestrated objective reduction, which suggests that consciousness arises from quantum processes within the brain. Why it's fascinating? If the brain operates on quantum principles, it would mean that our minds could be far more complex than we currently understand. It might also explain the subjective quality of consciousness, why we experience thoughts and emotions rather than simply processing information like a computer. Questions to ponder. If quantum mechanics is involved in consciousness, could we ever fully understand how thoughts arise? Could quantum processes help explain the hard problem of consciousness? Why subjective experience arises from objective brain activity? Panpsychism and quantum physics, consciousness in every particle. Panpsychism is the philosophical theory that consciousness is a fundamental property of all matter. In other words, everything down to the tiniest particle has some degree of consciousness. Some proponents of this view argue that quantum mechanics could provide the framework for understanding how consciousness pervades the universe. Simplified explanation. Imagine you have a drop of water. In classical physics, you could describe it purely by its physical properties, its weight, its temperature, etc. But what if, on a deeper level, the molecules inside the water also had an awareness of their environment? Panpsychism suggests that consciousness isn't limited to humans or animals. Instead, it's a fundamental feature of the universe. Quantum connection. Quantum mechanics hints at the idea that consciousness could be an intrinsic feature of matter. For example, quantum coherence, the ability of particles to remain in a superposition of states, could be the physical manifestation of a deeper, universal consciousness. This idea aligns with David Bohm's theory of the implicate order, which suggests that everything in the universe is interconnected through a deeper layer of reality that could also involve consciousness. Why it's fascinating? If consciousness is embedded in the very fabric of matter, it suggests that the universe itself could be conscious. In this view, every atom, every photon, and every quark might have a tiny, rudimentary form of awareness. This could radically change how we think about the mind-body problem and our relationship with the universe. Questions to ponder. If every particle has consciousness, does that mean we are connected to everything around us in a profound way? Could quantum processes in particles explain the nature of subjective experience? Integrated Information Theory, IIT. Could the universe itself be conscious? One of the most ambitious theories of consciousness is integrated information theory, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness arises from the degree to which a system can integrate information. The more interconnected and integrated the system, the more conscious it is. This theory suggests that consciousness might not be limited to humans or animals, but could be a property of any system that integrates information in a sufficiently complex way. Think of a light bulb. When it's on, it illuminates the room, but when you turn off the switch, the light goes out. In a way, the light bulb integrates the flow of electricity, but it's not conscious. Now, imagine a more complex system, like the brain, which integrates vast amounts of information across billions of neurons. According to IIT, the more information that's integrated, the higher the level of consciousness. Quantum connection. If IIT is correct, and consciousness is about integrating information, then quantum mechanics could play a key role. Quantum coherence, the ability of quantum systems to remain in a state of superposition and interact with one another, might allow for a higher level of information integration. In this way, the quantum world might help explain the emergence of consciousness in complex systems. IIT could provide a framework for understanding not only human consciousness, but also the consciousness of the universe itself. If the universe is a vast network of interconnected systems, each integrating information in complex ways, could it be that the universe itself has some form of awareness? Questions to ponder. If IIT is correct, could the universe be conscious in the same way that our brains are conscious? What would it mean if the universe as a whole had an awareness of its own existence? In this section, we've explored how quantum mechanics could be linked to consciousness, offering new possibilities for understanding the mind. From the idea of the brain operating as a quantum computer, to the radical suggestion that consciousness may be a fundamental property of matter, quantum theory opens up new avenues for thinking about awareness and existence. Quantum mechanics, with its strange and counterintuitive properties, challenges our understanding of reality, and in doing so, it may be pointing us toward a deeper, more interconnected view of consciousness. If consciousness arises from quantum processes, the universe might be far more conscious than we ever imagined, perhaps even in ways we are yet to comprehend. Quantum mechanics and time. Time is something we all experience: seconds ticking by, days passing, and memories fading as the years go on. But quantum mechanics suggests that time might not be as straightforward as we think. In fact, quantum theory challenges our most basic understanding of time, raising deep philosophical questions about its true nature. Could time be more fluid than we've ever imagined? Is it a fundamental part of the universe, or could it be an illusion? In this section, we'll explore how quantum mechanics reshapes our concept of time and what it means for our understanding of the universe. Non-linearity of time. Does time flow in one direction? In classical physics, time flows in one direction from the past to the future. This idea is deeply rooted in the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time, creating a natural arrow of time that moves forward. However, quantum mechanics presents a different picture. At the quantum level, time may not flow in a strict, linear fashion. Imagine you're watching a movie. As the story progresses, things happen in sequence: first this, then that. But at the quantum level, the sequence of events might not always be fixed. It's as though you're watching a movie where the scenes could play in any order, and the story might change depending on your perspective or how you're observing it. Time itself could be much more flexible than we experience it in our daily lives. Why it's strange: in quantum mechanics, particles don't always behave as though they follow a strict timeline. For instance, certain quantum processes can seem to reverse time, where particles appear to go backward in time, which challenges the idea of a universally directed flow of time. Quantum mechanics example. Quantum particles can travel backward in time according to the Feynman diagrams in quantum field theory. These diagrams depict particles as traveling through both forward and backward directions in time, essentially reversing the arrow of time under certain conditions. Questions to ponder. If time can flow backward at the quantum level, what does that say about our perception of the past, present, and future? Could the experience of time we have in our everyday lives be an illusion, a consequence of our limited perspective? Time reversal symmetry. Could time run backward? One of the most mind-bending implications of quantum mechanics is the idea of time reversal symmetry. This principle suggests that the laws of physics are the same whether time flows forward or backward. If you could rewind a quantum process, the physics would work just as they did going forward. In other words, if you could reverse the motion of a quantum system, it wouldn't violate any physical laws. Think of a video of a ball bouncing. If you play it backward, the ball seems to jump up from the floor, defying gravity. But in the quantum world, the ball's behavior would not change if played backward. The particles and forces involved would still obey the same fundamental rules, whether time is moving forward or backward. Why it's strange, time reversal symmetry in quantum mechanics challenges our everyday experience. We never see time rewinding in the macroscopic world. We observe things breaking, aging, and decaying in one direction only, forward. Yet, at the quantum level, particles behave as though they could reverse direction, suggesting time itself may be a construct based on our perception. At the subatomic level, certain particles like photons and electrons behave symmetrically under time reversal. If you were to reverse the direction of time for a quantum event, the system would evolve in precisely the same way, leading scientists to wonder if time's flow is an artifact of our observations. Questions to ponder. If time is reversible at the quantum level, does that mean our concept of time itself is just a mental construct? Could this symmetry have real-world consequences, such as in the development of time travel technologies? Quantum time travel. Is time travel possible? Could quantum mechanics make time travel possible? While time travel has long been a staple of science fiction, quantum mechanics opens the door to a theoretical possibility. The strange behaviors of particles at the quantum level, like superposition and entanglement, suggest that time may be more flexible than we realize. Could we, in theory, travel backward or forward in time? Simplified explanation. Imagine you're standing at a fork in the road, and both paths lead to the same destination. In classical physics, you can only take one path, but in the quantum world, there's a chance both paths are traveled simultaneously, with each one existing in a different timeline. It's as if you're living in two parallel realities, one where you choose one path, and another where you take the other. While actual time travel is still the stuff of fiction, some theoretical physicists suggest that quantum mechanics could allow us to move through time in ways we can't fully comprehend yet. One of the key ideas here is wormholes, theoretical shortcuts in space-time that could allow travel between different points in time and space. Quantum mechanics example, a specific type of quantum phenomenon called closed time-like curve suggests that time loops where the future influences the past could exist within the framework of general relativity. These theoretical time loops have been studied in the context of quantum particles, and they might be the key to understanding time travel. Questions to ponder. If quantum mechanics allows for time loops, could we travel back to the past and change history? What would happen to the laws of causality if time travel were possible? Quantum mechanics fundamentally challenges our understanding of time. From non-linearity to time reversal symmetry and the possibility of time travel, quantum theory presents a view of time that's far from the fixed, unidirectional flow we experience in our daily lives. At the quantum level, time is not an absolute, steady force, it's a malleable, fluid aspect of the universe. As we continue to explore the relationship between quantum mechanics and time, we may find that our perception of reality itself is shaped by deeper, quantum-level processes. Perhaps in time, the mysteries of time travel, time reversal, and the true nature of temporal flow will be unraveled, giving us an entirely new perspective on our place in the universe. The future of quantum science. Quantum mechanics isn't just about understanding the fundamental nature of reality, it's driving the next technological revolution. While we've already explored some of the mind-bending concepts that quantum mechanics presents, its potential applications in the future could change everything from how we compute to how we communicate. This section explores the cutting-edge developments in quantum science and what they might mean for the future of humanity. Quantum computing, the next leap in technology. Quantum computing harnesses the strange properties of quantum mechanics, such as superposition and entanglement, to solve problems that classical computers simply cannot. Unlike classical computers, which process information as bits, either 0 or 1, quantum computers use quantum bits or qubits, which can represent both 0 and 1 at the same time due to superposition. This gives quantum computers the ability to perform many calculations simultaneously, opening up possibilities for solving complex problems in seconds that would take classical computers millennia. Think of a classical computer like a person who can only check one box at a time on a list. A quantum computer, on the other hand, can check all the boxes at once, dramatically speeding up problem-solving processes. Quantum computers could revolutionize fields like cryptography, material science, drug discovery, and more. Problems that are currently intractable, such as simulating molecules for new drug compounds or optimizing complex systems, could soon be solved by quantum computers. Example: Google's Sycamore quantum processor achieved quantum supremacy in 2019 by solving a problem that would have taken the world's most powerful classical computer 10,000 years to solve within just 200 seconds. This marked a significant milestone in demonstrating the real-world potential of quantum computing. Questions to ponder. How soon will quantum computers be able to solve practical problems we cannot yet imagine? What ethical implications could arise as quantum computing accelerates developments in fields like artificial intelligence and cryptography? Quantum cryptography, the future of secure communication. Quantum cryptography uses the principles of quantum mechanics to create secure communication channels that are theoretically impossible to hack. The most famous application of quantum cryptography is quantum key distribution (QKD), which allows two parties to exchange encryption keys securely. If anyone tries to intercept the communication, the quantum system detects the intrusion and changes the key, rendering the hack useless. Simplified explanation: imagine sending a secret message inside a sealed envelope. In classical systems, if someone intercepts the envelope, they can open it and read the message. In quantum systems, if anyone tries to open the envelope, the quantum properties ensure that the contents are changed, making it obvious that someone was tampering with the message. Quantum cryptography could lead to virtually unbreakable security systems. Governments, banks, and organizations could use QKD to ensure that sensitive data remains protected from hackers and cyber threats, even in a future where supercomputers could break current encryption methods. Example: in 2017, China launched the world's first quantum satellite, which successfully demonstrated the use of QKD to establish secure communications between ground stations. This marked a significant step toward the global deployment of quantum communication systems. Questions to ponder. How will quantum cryptography change the way we think about privacy and security in the digital age? Could quantum communication lead to a new era of trust and transparency in global systems? Quantum sensors, revolutionizing measurement and detection. Quantum sensors leverage the unique properties of quantum systems to make incredibly precise measurements that classical sensors cannot achieve. These sensors can detect incredibly small changes in magnetic fields, gravitational waves, and even time. They hold the potential to revolutionize fields like navigation, geology, and medical diagnostics. Imagine you're trying to measure the tiniest vibrations on a surface. A classical sensor might miss the smallest signals, but a quantum sensor, like a super-sensitive microphone, can pick up every detail no matter how small. This precision opens up entirely new possibilities for measuring forces in the universe. Quantum sensors could allow for GPS-independent navigation, where extremely precise measurements of gravitational fields can track positions without relying on satellites. Additionally, quantum sensors could lead to breakthroughs in medical imaging, allowing for earlier detection of diseases or abnormalities on a molecular level. Example: quantum gravimeters are already being used to measure the Earth's gravity with extreme precision. This could help scientists detect underground resources, map geological structures, or even monitor natural disasters like earthquakes and volcanic eruptions in real time. Quantum energy, harnessing the power of the quantum world. One of the most ambitious goals of quantum science is to harness quantum effects to create more efficient energy systems. For example, quantum mechanics could play a role in developing quantum batteries, or improving solar panels by using quantum properties to capture more light and convert it into energy. Simplified explanation: imagine a solar panel that works like a sponge, absorbing as much sunlight as possible. Using quantum mechanics, we could make the sponge much more efficient, allowing it to soak up more light and convert it into usable energy. Example: researchers are already experimenting with quantum dots, tiny semiconductor particles that can capture sunlight at higher efficiency than traditional solar cells. These breakthroughs could help make renewable energy more efficient and affordable, accelerating the shift to cleaner energy sources. Questions to ponder: could quantum energy solutions help us tackle the global energy crisis? How soon could quantum energy technologies become commercially viable, and what impact will they have on the environment? Quantum science is not just a theoretical pursuit, it's the gateway to a new technological era. From quantum computing and cryptography to the development of ultra-sensitive quantum sensors and more efficient energy systems, quantum mechanics holds the potential to revolutionize how we live, work, and interact with the world. While these technologies are still in the early stages of development, they're already showing promise. As we continue to unlock the secrets of the quantum world, we may find ourselves on the cusp of breakthroughs that will shape the future in ways we can't yet fully imagine. Real-world applications of quantum mechanics. Quantum mechanics, with its strange and fascinating properties, is not just a theoretical framework, it's already making an impact in the real world. While much of quantum physics seems abstract and theoretical, its principles are increasingly being applied to solve practical problems. From revolutionizing medical technologies to transforming how we navigate and communicate, quantum mechanics is paving the way for groundbreaking innovations that could change the way we live. In this section, we'll explore some of the most promising real-world applications of quantum mechanics and how they're already shaping industries and research. Quantum medical imaging, a new frontier in diagnostics. Quantum mechanics is starting to make its mark in the medical field, particularly in medical imaging. Quantum technologies, such as quantum sensors, can provide unprecedented sensitivity in detecting tiny changes in biological systems. This could lead to more accurate and earlier detection of diseases like cancer, neurological disorders, and heart disease, potentially saving lives by spotting issues before they become critical. Simplified explanation: imagine you're using a flashlight to find something in a dark room. A regular flashlight gives you a basic view, but a quantum-enhanced flashlight would shine far brighter and reveal even the smallest details, allowing you to spot objects in the room with incredible precision. In medical imaging, quantum-enhanced tools could detect even the faintest changes in the body. Quantum sensors could make medical imaging more sensitive and accurate, enabling doctors to detect problems at earlier stages when treatment is more effective. For example, quantum imaging could help in detecting early-stage cancer, monitoring brain activity, or tracking the effectiveness of treatments for chronic conditions like Alzheimer's disease. One promising development is the use of quantum magnetometry, which can measure magnetic fields with extreme precision. This could help detect the subtle changes in the brain's magnetic field that may indicate neurological disorders or even predict seizures in epileptic patients. Questions to ponder: how could quantum-enhanced medical tools change the way doctors diagnose and treat diseases? What impact could early detection of conditions like cancer have on survival rates? Quantum energy solutions, harnessing the power of the quantum world. Quantum mechanics could play a key role in solving one of the world's most pressing issues: energy. By exploiting quantum effects, scientists aim to create quantum batteries and improve solar energy systems, making them vastly more efficient than current technologies. Imagine a super-efficient battery that can store more energy, last longer, and charge faster than anything we have today. Quantum mechanics might unlock the secrets to building such batteries, revolutionizing energy storage and making renewable energy sources, like solar and wind, more reliable and accessible. Quantum-based energy systems could lead to advances in energy storage, energy generation, and transmission, addressing the challenges posed by renewable energy and the increasing demand for power in a growing world population. Quantum technologies could enable smarter energy grids that optimize the distribution of power, potentially solving some of the biggest energy problems. Researchers are working on quantum dot solar cells, tiny particles that can absorb light more efficiently than traditional solar panels. Quantum dots could allow solar panels to capture more light, turning more of it into usable energy, which would make solar power far more efficient and cost-effective. Questions to ponder. Could quantum energy breakthroughs make renewable energy more reliable and sustainable? How soon could quantum energy solutions be available to the general public, and what would their impact be on the global energy landscape? Quantum navigation, beyond GPS and the digital revolution. Quantum mechanics is also revolutionizing how we navigate the world. Quantum sensors are already being used to create GPS-independent navigation systems. These quantum sensors can detect incredibly subtle changes in gravitational and magnetic fields, enabling highly precise positioning without relying on satellite signals. Traditional GPS relies on satellites orbiting the Earth to pinpoint your location. But quantum navigation systems could use ultra-sensitive quantum sensors to detect the Earth's natural magnetic fields and gravitational pull, allowing you to navigate with pinpoint accuracy whether you're in a dense forest, a submarine, or on another planet. Quantum-based navigation systems could eliminate the need for GPS satellites, which are vulnerable to interference and hacking. They could also enable high-precision navigation in places where GPS signals are weak or unavailable, like deep underground, underwater, or in space. Quantum gyroscopes, which use quantum entanglement and superposition to detect the rotation of objects, could be used to create extremely accurate navigation systems. These gyroscopes are already being tested in aerospace and defense applications, but their potential for everyday use, like in autonomous vehicles or deep-sea exploration, is enormous. Quantum computing in cryptography, the dawn of unbreakable security. Quantum computing is poised to revolutionize cryptography by providing the means to create encryption systems that are theoretically unbreakable. Traditional encryption methods could become obsolete as quantum computers gain the ability to break them, but quantum cryptography offers a solution by using the principles of quantum mechanics to secure data in ways that classical systems can't match. Current encryption relies on complex mathematical problems that are difficult for classical computers to solve. But quantum computers can solve these problems much faster. On the other hand, quantum cryptography ensures that any attempt to intercept or tamper with encrypted messages would be immediately detectable, making hacking virtually impossible. As cyber attacks become more sophisticated, quantum cryptography could offer a future-proof solution. It promises to secure everything from personal communications to banking transactions to national defense secrets without the risk of being hacked by even the most powerful computers. Example: in 2020, China's MISIS satellite successfully transmitted quantum encrypted data across thousands of miles, demonstrating the potential for secure global communication using quantum technologies. Questions to ponder. What impact will quantum cryptography have on online privacy and security? Could quantum encryption help protect sensitive data from cyber attacks in the digital age? As we've seen, the real-world applications of quantum mechanics are not confined to theoretical physics. Labs, they are already shaping industries, technologies, and even our daily lives. From revolutionary medical imaging and energy solutions to quantum navigation and unbreakable cryptography, quantum mechanics is poised to transform every aspect of society. The future is quantum, and as we continue to unlock the mysteries of the quantum world, the possibilities are endless. Whether in health, energy, security, or computing, quantum mechanics promises a future where science fiction becomes science fact. As we continue to explore and harness these extraordinary technologies, we may be on the brink of a new era of innovation that will change the world forever. The quantum journey ahead. Quantum mechanics has taken us on a journey through the very fabric of reality itself, a realm where the familiar laws of physics are challenged and the impossible becomes possible. From the mind-bending properties of wave-particle duality to the profound questions it raises about time, consciousness, and our understanding of existence, quantum science pushes the boundaries of human knowledge and invites us to think in ways we never have before. We've explored how quantum mechanics is reshaping not only physics but philosophy, asking whether reality exists only when observed, and whether every possible choice creates a new universe. We've delved into the potential connections between quantum processes and consciousness, raising the possibility that the universe itself could possess a form of awareness. We've seen that quantum mechanics isn't just abstract theory, it's already changing the world in concrete ways. Quantum computing promises to revolutionize industries by solving problems that are currently beyond our reach. Quantum cryptography is set to make communication more secure than ever before. Quantum sensors and energy solutions could transform healthcare, navigation, and our global energy systems. The future of quantum science is a thrilling one. While there is still much to learn, the breakthroughs we've discussed could reshape entire industries, solve some of the world's most pressing problems, and open up new frontiers in technology and human potential. As quantum technologies continue to evolve, we are standing on the brink of a new era, an era where the strange, wonderful, and mysterious world of quantum mechanics becomes an integral part of our everyday lives. But perhaps the most important takeaway is this: quantum mechanics teaches us that the universe is far more interconnected, unpredictable, and beautiful than we ever imagined. Whether we're trying to unlock the secrets of consciousness or exploring new technologies, quantum science reminds us that there is still so much more to discover. We are only beginning to scratch the surface, and the future holds infinite possibilities.